Okay, welcome to EGR 445, summer 22. In today's class, I'm gonna talk about something called as the worm and worm wheel. So design of worm and worm wheel. Sometimes worm wheel is also referred as just wheel. So the way it looks like is you have a wheel, which is a gear, and you have this worm. So as you can see, the biggest advantage of worm wheel is you would observe that the axis of rotation for the worm and the axis of rotation of wheel, they are in two different planes, and those planes are perpendicular to each other. So if you look at the wheel shaft, which is shown over here, and the worm shaft is shown in the bottom. So this is called as the worm. And this is called as the wheel. And the biggest advantage of worm wheel is a unidirectional power transmission. So what it means is if you connect a motor here, and if you connect some type of a load here, then you can rotate the worm in clockwise or counterclockwise direction, and the wheel would rotate in clockwise or counterclockwise direction. But you can't rotate a wheel and expect the worm to rotate. So the power transmission, if you think about the power transmission, it goes only in one way. So it goes from worm to worm wheel. And that is needed in certain applications. For an example, a load bearing application. So you want to lift, or if you want to hoist some load, and all of a sudden the electricity or the motor power is cut off, then you don't want that load to be freewheeling down and get someone injured. So that is the reason why the worm wheels are used in load carriage. Now, worm is something similar to a power screw. So when we look at the design of worm, it's going to be similar to the design of power screw. And wheel is like a gear. So in worm wheel, we are combining two design processes. One is design of power screw, and second one is design of wheel. The disadvantage of worm wheel is efficiency is low. So typically the efficiency is low. And because of that, what you have is you have heat generation. So when we design a worm wheel, we want to make sure that we are somehow able to dissipate that heat. So the lubrication becomes important, the design of casing becomes important, and the selection of lubricant is also is important. So what are the different types of worms? So if you look at the worm, there is something called as the cylindrical worm. You have a cylindrical worm, And then you have a conical worm. And as you can think about it, the cylindrical worm is like if you have a screw that is cut on a cylinder. So basically you have a cylinder and the screw is cut on the cylinder. And the conical worm is like, think about it like you have a cone and then you're cutting threads on the cone. Similarly, if you look at the worm wheel, or sometimes also just called as wheel, you can have a straight wheel, just like spur gear. You can have a hobbed wheel, and you can have a concave. So you can have a straight wheel, you can have a hobbed wheel, and you can have a concave wheel. Now, these are some of the concepts that are interchangeably used in design of worm and design of power screws. For an example, there is the concept which is called as the lead. So in worm, think about same as power screw. We have concept of lead. Lead is advancement per revolution. And there is the concept which is called as axial pitch. Which is also interchangeably used as the linear pitch, which is called as PA. Then concept of lead is axial pitch multiplied by number of starts. Then the third is the lead angle is equal to tan inverse of lead divided by pi times diameter of worm. And the last thing which I want to talk about, and it would be a good time to open up your textbooks and look at the table 31.1 is tooth pressure angle. So, and please look at table 31.1. So for this, you have the lead angle, and the lead angle, I just need to give you a pictorial representation. This is the lead. This is pi times diameter of worm. The lead angle can go anywhere between 9 to 45 degrees. So lambda and phi. So 0 to 16, 14 and a half, 16 to 25, 20 degrees, 25 to 35, 25 degrees, and 35 to 45, 30 degrees. So you would see this table. So 0 to 16 is the lead angle. And if your lead angle varies between 0 degrees to 16 degrees, the typical pressure angle is 14.5. As the lead goes on increasing, the pressure angle goes on increasing. Next thing is we have the concept of normal pitch. So what we have is we have normal pitch. And this is something we saw in the case of helical gears. The pitch in the normal direction, which is Pn, is equal to Pa cosine lambda. And the last part is the velocity ratio. That is the speed of revolution of worm divided by RPM of wheel. And clearly, as you can notice, the worm RPM is going to be greater than the wheel RPM, which is equal to the diameter of the wheel divided by diameter of the worm. So think about this like Vp is equal to N times D, where N is the speed, D is the diameter worm, which is equal to N times D wheel. So that is something that you should keep in mind. Now, depending upon the velocity ratio, you have some recommended number of starts. So if you have a low velocity ratio, then you can work with just a single start worm. If you have a higher velocity ratio, then it's advised to go with the multi-start worms. So for that, again, I'm gonna recommend you all to just take a look at this table 31.2 from the textbook. And in table 31.2, you have this velocity ratio versus number of starts. So velocity ratio, number of starts, you have 36, 1, 12 to 36, 2, and now sometimes this is a little bit confusing, and I'll explain it to you why. So again, say if you have number of start, I mean the velocity ratio is 12. So if you have a velocity ratio 12, then you can choose. You can have two start, a double start screw, or triple start screw. If you have a velocity ratio 36, then you can have a single start screw, or you can have multi-start screw. But again, these are these open-ended design guidelines. So you, as a designer, the choice is yours. you can decide how many start screws that you want to use, what application you want to use, and how do you want that design to work and look. So this is completely up to you. The next part is if you look at the wheel or the worm wheel. So worm wheel design. It's based on the worm design. So always what you do is you first design or get some preliminary dimensions for the worm, and then that actually gives you overall dimensions of the wheel. So here are some classic dimensions. So normal pressure angle is 14.5, and it can be 20 degrees. Okay, my apologies for that interruption. So normal pressure angle is 14.5, 20 degrees. You can have an outside dia, which will be dg plus dc. Then you can have a throat dia, which is 2.5 pc plus maybe some clearance. And then you can have a gear face dimension, which is 0.8 pc plus some clearance. And then you can have a gear rim, which is 2.2 times pc plus some clearance. And overall, these proportions are given in table 31.4. So if you have a textbook, I'll quickly take a look at this. Then, as I talked about in earlier slides, that heat generation is a problem because the worm wheel drives are not very efficient. They generate a lot of heat. So we need to check for heat dissipation. So check for heat dissipation. So Q loss is equal to 1 minus efficiency times the power that is transmitted, and that we have to equate to H times A times delta T. So where H is the coefficient of heat transfer, A is the area and delta T is change in temperature. So one thing I want you to understand that whenever we are designing, the worm is usually a very strong component, because if you think about the worm is cut into from a solid shaft. So wheel is weaker than worm. So what that means is always for worm wheel, the wheel is designed and worm dimensions are decided based on wheel. So if a reduction ratio is given or the velocity ratio is given, you have sort of a proportion or what should the diameters look like. If the center distance is given, you have some idea that what should be the approximate dimensions. But once you start the actual design process, since the wheel is weaker than worm, we always design the weaker element. So worm gear or the worm wheel is designed. So what are the design steps to design a worm wheel? And these steps are exactly same as design of spur gear. So wheel design is similar to spur gear design. As a matter of fact, it is actually simpler. So step one. Step one is we have to find out the value of WT, which is P divided by V multiplied by the service factor, where WT is the tangential load. Step two is WT is equal to sigma naught times CV times B times pi times M times Y, and CV is 6 divided by 6 plus V, and Y is equal to, again this is Lewis's form factor, value of Y is going to be 0.124 minus 0.684 divided by number of teeth on wheel. This is for pressure angle 14.5, and 0.154 minus 0.912 divided by T for pressure angle of 20 degrees. Following next step, step 3. Determination of dynamic load. And it's very simple. WD is equal to WT divided by CV, where CV is equal to 6 divided by 6 plus V. So you don't have to use that long Buckingham equation. What you can do is you can just find out the value of velocity, CV, and then just use the velocity factor CV, and then you can actually get the value of WD. Next step, step 4. We have to find out the static load. And for static load, Ws is equal to sigma E times B times pi times M times Y. And typically the worm wheels are made up with two materials majoritarily. One is cast iron, which is 68 Newton per millimeter square is the value of sigma E. And the second one is Prosper bronze, is 168 Newton per millimeter square. And for safe, Ws has to be greater than WD. And the last part is determination of wear load. Which is WW. And this is very simple, which is DG, which is the diameter of the gear, multiplied by the face width, multiply this factor K. And this factor K can be found out from the textbook. So for an example, and it's actually super simple. So if you look at the worm, you look at the wheel and K. So if you have a steel worm and you have a Prosper bronze wheel, which will be 0.415. If you have a cast iron worm and Prosper bronze wheel is 1.035. And next, step 6. Is heat dissipation. So what we do is we find the heat that is generated, and that is 1 minus efficiency multiplied by P. And efficiency for particular type of worm wheel, you can look at the table, or there will be a chart that actually will show you how to the typical values of efficiencies. And then you have to find out Q capacity, which is how much heat can be dissipated by that geometry, which is H times A times delta T. And area, if nothing is given, you can just assume pi times diameter of the wheel to be multiplied by B as area. This is the heat transfer coefficient. And that is the change in the temperature. So this worm wheel design is actually super simple. And what I would do now is let me quickly work out a problem. Any questions on worm wheel design? So let me work out a simple problem. It's a design problem. Okay, there is a question in the chat window. Okay, no, comment. Okay, fantastic. And if you have the textbook, I just want to quickly go through the charts in the textbook. So if you have a minute, please look at the textbook. On page 1104, you would see the lead and the relationship between the lead angle and the pi times TW. Table 31.1 gives you different values of lead angle and their relationship with pressure angle. 31.2 table gives you the velocity ratio and the number of starts on the wheel. Then you have proportions of worm in table 31.3 that we talked about. Then in table 31.4, you have proportions of worm gear, where you have the normal pressure angle. Then you have the long expression for efficiency. And this equation for efficiency, as you can see, is purely dependent on the lead angle, the pressure angle, and the coefficient of friction. So I'll just write this equation down. There's also a plot that kind of gives you the efficiency, but efficiency is tan lambda cosine phi minus mu cosine lambda divided by cosine phi tan lambda plus mu. So where lambda is equal to the lead angle or the helix angle, phi is the pressure angle, and mu the coefficient of friction. So, and many a times value of mu is not given. So nothing wrong in assuming value of mu to be like 0.2 or 0.3, or if you have a well lubricated worm wheel, then it can go all the way up to 0.01. So for well lubricated, and 0.1, say not well lubricated. If you want to be super duper accurate, the value of mu can be dependent on the rubbing velocity. So 0.275 divided by VR 0.25. For rubbing velocities, or the velocity ratio, the pitch line velocity of 12 to 180. And mu is equal to 0.025 plus VR divided by 18,000 for speed more than 180 meters per minute. So these are the equations. There is one more approximation that we can potentially use. So this is the efficiency approximation. So if you want to approximate the efficiency, which would be 1 minus mu tan lambda 1 plus mu divided by tan lambda. So typically this will go somewhere between 86%. This is typical. So what you can do is you can assume the efficiency to be between 0.85, 0.8 to 0.85, and then use that as a benchmark to do some preliminary calculations. Now, I think with this, we should be able to solve the problem. And there is some criteria which is called as the worm gear design curves. And worm gear design curves are nothing but it kind of gives you the relationship between the normal pitch, center distance, lead angle, and appropriate velocity ratios. So just some additional guidelines. So additional guidelines. These additional guidelines are like, if you have a worm wheel, that worm wheel is meshing with a worm. So this is the worm. The center distance is this. This is the center distance, x. And then what you have is you have this as the normal pitch. So x, which is the center distance, is diameter of the worm plus diameter of the wheel divided by 2. And what you do is, there is a chart wherein we have the lead angle on x-axis. We have x divided by ln on y-axis, and then there are these different velocity ratios. So say this is velocity ratio is equal to 20. This is velocity ratio is equal to 4. And then you have these different lead angles. So 10, 20, 30, and so on and so forth. And then you have this 1, 3, 5, etc., etc. So what you can do is this kind of gives you some dimensions to start with. If you know your velocity ratio, if you know the ratio between x and ln, then you can actually determine what should be your lead angle, what should be the velocity ratio, and so on. So it totally depends upon design. Many a times, one or more design parameters are fixed because that's what we want for design. Or sometimes as a designer, you have to go and select certain parameters and then make some decisions so that how that design would look like, and then find out the dimensions. So what I would do now is actually I will work out a problem. And again, I tell you, for as in design or for worm build design, there are multiple ways of designing. So there is no like just one standard way. You can follow different design process. As a matter of fact, if you look at the problems that are worked out in the textbook, each problem is worked out using different techniques. And again, but they all use the information and the design tables that are given in the textbook. So let me work out a very simple problem. So design a worm wheel to transmit P is equal to 10 kilowatts, and the worm RPM is equal to 1400, and speed reduction is equal to 12:1, and the distance, center distance, is 25 millimeter. So at this point, we can actually work out this problem. And pressure angle, let's assume the pressure angle to be 20 degrees. So let's assume to be pressure angle is equal to 20 degrees. And at this point, we have a lot of options. So what we can do is we can start with the ratio of x divided by ln. And the idea is we want to find out x divided by ln to be as low as possible. X divided by ln, this ratio can be determined from the chart that we have over here. We have one more equation that we can use, which is dw plus d wheel divided by 2 is equal to 225. So I just want to give you this x divided by ln. This equation comes from the formula 1 divided by 2 pi 1 divided by sine lambda plus velocity ratio divided by cosine lambda. So the chart that you see here, the equation for this chart is shown over here. Now velocity ratio, there's another equation for the velocity ratio, which is 1 divided by tan cube lambda. So 12 is equal to 1 divided by tan cube lambda. So from here, the value of lambda can be found out as 23.6 degrees. And you can take this 23.6 degrees lambda over here and draw a vertical line. So this is lambda is equal to 23.6. The velocity ratio is 12. So for example, this is the velocity ratio 12 line. And from here, you can find out the value of x divided by ln. And for this x divided by ln, so x divided by ln is equal to 2.5. And with this, we know x, which is center distance, which is 225 divided by 2.5 is equal to ln, and ln is equal to 90 millimeter. And L is equal to ln divided by cosine of lambda, 90 divided by cosine of 23.6, that gives me 98 millimeter. Now the next part is the velocity ratio is given as 12. Velocity ratio is given as 12. So we have to find out appropriate number of starts. So as you can see, you can go to the table 31.2. So number of starts is equal to 4. So we can assume the 4 number of starts. So we can find out the pitch. Pitch is equal to lead divided by number of starts. The lead is 98.2, 98 divided by 4, which is about 24.5. Then with this, you can find out the value of module, which is PA divided by pi, which is 24.5 divided by pi. That gives you 7.8 millimeter. And with that, the axial lead and other values can be found out, but please try to understand the 7.8 is a non-standard dimension. So what we will do is we'll round it off and we would say assume module is equal to 8 millimeter. And once you do the module is equal to 8 millimeter, you can find out the value of axial pitch pi times m, which is 25.13 millimeter. Then you can find out the value of L, which is PA times 4, which is 100.5 millimeter. and you can find out the actual center distance, and then you can find out the diameter of worm wheel, and so on. So at this point, you can find geometrical parameters. So the basic dimensions are known once you know the module. Now, what we want to do is, here we start the actual design. So here, in the first part, what we have done is we were given the speed reduction ratio. We were given the pressure angle. We used all this information to find out the overall dimensions. So what would be the appropriate dimensions to meet these speed reduction requirements and the center distance requirement? And this actually gives us the geometry of the worm and worm wheel. Now, what we can do is we can actually proceed to the actual design, and the design is always done on the wheel because the worm is stronger than wheel. So we design wheel. So step one, we know the overall dimensions. So module is 8 millimeter. We know the number of starts multiplied by, we know the reduction ratio. So we know the overall dimension of worm wheel. Then we can find out the tangential load, and the tangential load WT can be found out using the power transmitted divided by Vt, or the velocity V multiplied by CV. So WT is equal to the power, that is 15 kilowatts, 10 kilowatts, 10 to the power 3 divided by the speed, which is pi times d times n divided by 60 multiplied by the service factor 1. So once you put these dimensions in, you get 4260. Next is the velocity factor CV, is 6 divided by 6 plus V is equal to 6 plus 2.35 is equal to 0.72. And the Lewis's form factor for 20-degree involute tooth, which is the value of y, is 0.154 minus 0.19912 divided by TG, 0.154, 0.912 divided by 48 is equal to 0.135. So basically TG is equal to n multiplied by the velocity ratio. So n is equal to 4, velocity ratio is equal to 12, so we got 48. And the worm is made up with, say, steel or cast iron, but we are going to assume the wheel made with phosphor bronze. And for that, we assume sigma O is equal to 84 Newton per millimeter square. This comes from the data book. So WT is equal to sigma naught multiplied by CV multiplied by B multiplied by pi times 8 multiplied by pi. Now in this case, if you look at the first step where we decided or we found out all the principal dimensions. So what I'm going to do is I'm just going to substitute these values and then find out what is the value of WT. So sigma naught is 84, CV is 0.72, 59, pi 8, 0.135, and which is 12,110 newtons. Now, so this is WT, and this WT is much greater than the actual WT, which is WT actual, which is we found out to be 40 to 60. So what that means is this design is going to be safe. So let's try one more time. So we will find next step, which is determination of dynamic load is WD. WD is WT actual divided by the value of CV. So the WT actual is 42.60 divided by CV is 0.135. So you will get value of dynamic load. Then determination of static load. So which is WS, and WS is sigma E times B times pi times M times Y. Sigma E for phosphor bronze is given as 168. So you have 168 times 59 times pi times 8, 0.135. So which is 33 kilonewtons. So which is greater than WD. So safe. The next step is find WW. Where load is WW is equal to DG times P times K, which is 384 times 59 multiplied by 0.55, which is 12 kilonewton. And this is greater than WD. So it is safe. A word of caution. Same problem is solved in the text, but textbook solution is incorrect. So please try to understand. This is the way this problem has to be solved. And that's why I wanted to take this problem very specifically. So, and I will, if you have the textbook, I would encourage you to see the issue with the solution in the textbook. So in this problem, we are asked to design a worm wheel. Now the first step is okay. So the velocity ratio is 1 divided by tan cube lambda. So from the velocity ratio, we can find out the value of lambda. Once the lambda is known, the velocity ratio is known, we can use this chart to find out the optimal x divided by ln. So the ratio of the center distance by the normal pitch. That also is fine. So with that, we should be able to get the value of normal pitch. With the normal pitch, we should be able to get the value of, the lead, and then we should be able to get the value of normal, the axial lead, and then we should be able to get the value of axial pitch, and from axial pitch, we should be able to get the value of module. Once the module is known, we can round off the module and determine all the dimensions. So please understand, pretty much at this step, the worm wheel is designed. Worm and wheel is designed. But this design does not involve any stress calculations. This worm wheel is designed based on the geometry, the center distance. But we need to make sure that whatever design that we have is safe to transmit the required power. So what we need to do is we need to find out the tangential force. And the equation for tangential force is power divided by pitch line velocity multiplied by the coefficient of velocity, CV. And then we find out the Lewis's form factor, and we find out the number of teeth on the gear is number of starts multiplied by the velocity ratio. And we assume that the wheel is made up with crossover bonds. Now, at this point, what we do is we find out what is the WT that this wheel can support. So essentially, if you look at sigma naught, say CV, value of B, all these values are already known. So we know that this wheel that we have designed based on the geometrical parameters is able to transmit 12 kilonewtons, which is much more than the required 40 to 60 newtons or 4.2 kilonewtons. That means this assembly is safe. Now we want to find out the dynamic load. The dynamic load is found out from the actual load capacity. So the actual loads that is being transmitted, and not, so WD is, you shouldn't find out from WT, which is maximum. So which is 12 kilonewton, and that is what the book did. So this is incorrect. So you have to find out the dynamic load from the actual WT that is transmitted. And the next step is we need to find out the static load, and this static load is the maximum load that that wheel can sustain, which is 33 kilonewton, which is significantly higher than this dynamic load, which is shown over here. And that is how we can actually find out the solution. And then next thing is we find out the wear load, and the wear load should be greater than the dynamic load. So please keep that in mind when you work out the working problem, or for that matter, when you refer the textbook for the worm build design. The next step is we need to check for the heat dissipation. And to check for the heat dissipation, what we need to do is, there are multiple ways of doing this. What you can do is, we can assume the equation for the efficiency, an approximate equation for the efficiency, which is 1 minus mu tan lambda divided by 1 plus mu tan lambda. So efficiency is equal to 1 minus mu tan lambda divided by 1 plus mu divided by tan lambda, and you can assume mu to be 0.01 and find out the efficiency, and then you can find out the power loss as heat is equal to 1 minus efficiency multiplied by power transmitted, and that should give you approximately, let me see, the efficiency is about 89%, so 1 minus 0.89 multiplied by the power, which is 10 kilowatts. So the heat generated is equal to 1375 watts. And then what we do is we find out the approximate area. And you can think about the approximate area is, you have this wheel, you have this worm. So, and there are different ways you can actually consider this area, and you can consider this area of the worm. So you can have total area, A total is equal to A worm plus A field, and I'm gonna give you expression pi by 4 dw square plus pi by 4 dg square, and that somehow comes around 115,827 millimeter square. Sorry, this comes to about 120,000. And then you can find out the Q dissipated is equal to A delta T times H, and substitute the value of 120 10 to the minus 6 delta T multiplied by H 378, and that approximately will go somewhere between delta T is equal to 30 degrees. So that is how that design would look like. And the next few steps are design of shafts, and the design of shaft is similar to the design using the torque and the bending considerations. And I would encourage you to take a look at the textbook and follow the shaft design from there. Okay, at this time, we are going to take a break of 15 minutes, and then we'll be back. and I will start the discussion on the internal combustion engine. So we are going to look at something called as internal combustion engine. So first, let me talk about the difference between external combustion engine and internal combustion engine. So engine is something that will generate mechanical energy. So, I mean, for an example, you can think about a steam engine, wherein what you have is you have a boiler, and then you have this external source or heat. You heat the water, that get converted to steam, and this high pressure, high temperature steam goes to a steam engine, and this steam engine, there will be a crosshead, and then what you have is this, you have the exhaust, and then you have some sort of water reservoir, this would be the boiler, this is the steam engine, and that is how you can convert. This is the combustion chamber. So what you have is you have this system wherein the working fluid, which is water gets heated all the way to the gaseous stage where you have steam. That high temperature, high pressure steam gets expanded in this engine, and you have mechanical work, and then you can actually have this mechanical work doing something like producing electricity if it is connected to a generator, or used for locomotion like the steam engine. And what is the advantage of external combustion engine? In external combustion engine, no restriction on fuel. So which means if you want to burn gas, you can burn gas. If you want to burn wood, you can burn wood. If you want to burn twigs, you can burn twigs. You can burn anything that you want. Then it can be used for a lot of applications like locomotion, like steam engines, but it can be used for the power generation. It can be used for doing some other useful work like farming applications, pumping applications, and so on. So applications are vast. But what are the major disadvantages? Major disadvantages is it's bulky. That's why we don't use external combustion engines in automobiles. I mean, when automobiles started, some automobiles were built with boiler and external combustion engines, but nowadays we look at the internal combustion engines. Typically, the external combustion engines work on like a steam engine. Steam engine works on the Rankine cycle. So if you look at the PV diagram of the Rankine cycle, it's something like this. So the area under the curve is the work done. Now, in contrast with the internal combustion engine, the way internal combustion engine works is you have the working fluid that is burnt inside the cylinder, not outside the cylinder. So if you think about an internal combustion engine, what you have is you have the inlet valve, you have the exhaust valve. So this is the inlet valve. This is the exhaust. And what happens is through the inlet, you have either the fuel or L fuel mixture coming in. So there are two types. One is a gasoline engine or gas engine. And the other one is diesel engine. So in gasoline engine, what you have is you have the air fuel mixture that comes through the inlet, and then this air fuel mixture is compressed, and then at the end of the compression you have the air fuel mixture which is at high temperature and high pressure. You have a spark plug that ignites the air fuel mixture, and after the ignition that work is done. So basically this piston is pushed down, and at the end of the expansion stroke, you have an exhaust stroke wherein the fluid, which is actually spent, the gases, they basically are thrown out of the exhaust port. So there are 4 strokes actually. So or the cycle is something like suction, compression, expansion, and finally what you have is exhaust. So these are the 4 stages of internal combustion engine. So in suction, the piston goes from something called as the top dead center, TDC to BDC, and the fresh charge is sucked into the cylinder cavity. In compression, the piston goes from bottom dead center, which is BDC, to top dead center, and the charge is compressed. As the piston hits the TDC, the spark plug, this is the spark plug, generates a teeny tiny spark that burns the charge, and you have this high pressure, high temperature gases that do the work on the piston, and then expansion stroke ends, and then in the exhaust stroke, the piston goes from BDC to TDC and the exhaust valve opens. So suction, compression, expansion, and exhaust, these strokes, they continue. As I said, for gasoline engine, let me show you how the pressure versus volume diagram looks like. This is pressure, this is volume. Okay, so first what you have is you have the suction, then you have the compression, and then you have the heat addition, expansion, and exhaust. So this is compression. This is where the spark is initiated. This is where the combustion kind of finishes. And then this is where the expansion takes place. And this is where the exhaust happens. So this is compression. This is heat addition. This is expansion. And then finally, what you have is you have exhaust. And then here, and then you have suction. So that is how the cycle completes. In the case of diesel engine, the strategy is slightly different. In the case of diesel engine, the air fuel mixture like gasoline engine is not present. So it just the air is compressed. And then at the end of the compression stroke, the fuel is atomized. The fuel is sprayed, or the diesel is sprayed onto the air, which is at high temperature and high pressure. And that diesel expands. I mean, the diesel combusts. And because of that, the whole thing sort of explodes and generates power. So in the case of diesel cycle, what you have is, so this is pressure, this is volume, you have suction, this is just air, you have compression, this is just air, and this is where the fuel is sprayed, so or atomized. So this is where you have the heat addition, and then what you have is you have expansion, and then you have exhaust. So this is how the diesel cycle looks like. So this is called as the gasoline cycle, or also called as Otto cycle. This is called as the diesel cycle. So you have suction, compression. This is where the heat is added, and this is where the exhaust takes place. This is expansion, then you have the exhaust. Now there is a combination cycle. So as you can see, the main difference between the gasoline cycle and diesel cycle is heat addition. So in the gasoline cycle, the heat addition is at constant volume. So heat added at constant volume. And here, heat added at constant pressure. There is something called as the dual cycle, wherein you have some heat that is added during the constant volume, and then some heat that is added during the constant pressure. But how would you distinguish whether it's a diesel engine or gasoline engine? One thing you would notice immediately is gasoline engines and diesel engines. Gasoline engines clearly runs on gasoline, or if you go to Europe, they call it petrol. Diesel runs on the diesel. The cycle is Otto cycle. The cycle is diesel cycle or dual cycle. In gasoline engine, you have a spark plug. And in diesel engine, you have the fuel atomizer or the nozzle or the sprayer. So then typically the gasoline engine compression ratio is low. You have high compression ratio. The efficiency is lower than the diesel. Efficiency higher than diesel. Then if you look at the gasoline engine, they are lighter and quiet compared to diesel. The diesel engines are bulky and noisy. Gasoline engine are less polluting. Diesel engines are, because of the soot and incomplete combustion, they are polluting. So think about the gasoline engine. Is the gasoline is already mixed with air and burnt. So usually at the end of burning, it's clean. That's why the exhaust coming from the gasoline engine is clean. If you look at the diesel engine, usually the exhaust gets fed into the exhaust treatment like diesel exhaust fluid, and then that exhaust is treated. If you take out the muffler or the exhaust treatment, you will see all that black soot coming out of the diesel engine. So diesel engines are polluting because not all the fuel is burnt. Because of that, the gasoline engine are used for low power application and high power application. So you will see all the trucks, semis, they use diesel engines, automotive cars, and small engines like a weed whacker engine and other engines, they use gasoline. So these are the main differences between two common types of engines. So let's talk about the components of engine. What are the components of engine? If you look at the engine will have a cylinder, then it will have a piston, there will be inlet plenum, there will be exhaust plenum, there will be valve, and assuming it's a spark plug engine, you will have a spark plug. I'm gonna call this spark plug. So there will be a cylinder, there will be a piston, there will be a connecting rod, there will be a crank, there is intake valve or inlet valve, and there will be exhaust valve. And usually there is something called as the crankcase, and there is oil. And this oil gets splashed onto the cylinder cavity, so that provides the lubrication. Now piston has some grooves and there are rings. They are called piston rings. So these are piston rings. So the purpose of the piston ring is functions. So the first and foremost, inlet valve opens, air fuel mixture enters, and the piston goes down. And then inlet valve closes, piston starts going up, it compresses the fluid, air fuel mixture, and the temperature goes up, the pressure goes up, and at the end of the compression stroke, the spark is ignited. After the spark is ignited, it takes the whole fluid, working fluid burns, there is a spontaneous combustion, and then because of that combustion, high heat is generated, high pressure gases are generated. Those high pressure gases generate the very extra high forces onto the piston, and that piston starts moving downward, and that is called as the expansion or power stroke, and that is the only stroke where the fuel energy gets converted to mechanical work. And in the last stroke, the piston again starts going from the bottom dead center to top dead center. Exhaust valve opens, and basically all that charge gets thrown out. So that is called as the exhaust. So this is called as a 4-stroke engine. In 4-stroke engine, 2 revolutions of crankshafts, accomplish suction, compression, expansion, and exhaust. So that's why this is called as a 4-stroke engine. 4-stroke engines are very efficient, and the engines that are used typically in cars, automobiles, or even motorcycles, those are 4-stroke engines. On the other hand, there is something called as the 2-stroke engine. So there is 2-stroke engine. In 2-stroke engine, what you have is out of these suction, compression, expansion, exhaust, two of the processes are performed in half a revolution of crankshaft, and 2 of the other processes are performed on the other revolution of the crankshaft. So think about it like, as the suction is happening on one side, the compression is happening on the other side. So in the case of 2-stroke engine, we don't have valves, but what we have is we have ports. So there is something like a transfer port. And what we have is we have something like this. This spark plug. And here I'm going to call this transfer port. So during the suction, the air comes in, air fuel mixture comes in from the top. This is where the suction is happening. At the bottom, already there is charge which is compressed. This compressed charge kind of goes up, and then the spark is ignited, and you get expansion. And then as the piston is going down, you have the exhaust. So the thing that happens in the case of two-stroke engine is like the four strokes, I mean the four cycles are completed in one revolution of the crankshaft. And so two-stroke engines are very compact. Two-stroke engines, unfortunately, they have little bit lower efficiency than four-stroke because there is something called as charge escapement, which means the fresh charge gets escaped through the inlet and exhaust port opening at the same time. So there's a two-stroke engine, but two-stroke engines are used in a lot of applications. Again, efficiency is low for two-stroke engine, but less moving parts. And more like more polluting. So there is pollution. And two-stroke engines are used typically for small scale applications. So for example, if you look at the weed whacker engine, or if you look at the old moped engines, or if you look at the old generator engines, those are all two-stroke engines. So two-stroke engines are commonly used for low power application. Four-stroke engines are used for typically the large power applications and higher efficient engines. But two-stroke engines are very reliable, less moving parts, but they are polluting. So you will see that two-stroke engines are not commonly used nowadays because of the pollution regulations. So these are the main important components of engine. Now I want to give you sort of what are the components that we are going to design. So when we have a problem, engine design problem, engine design means first we have to design the piston and cylinder. So typically we design cylinder first. We design cylinder, we design piston, then we design connecting rod, then we design crankshaft, then we design crank, then we design rocker arms and valves, and then we design cams. So first we design cylinder, then we design piston, then we design connecting rod, then we design crankshaft, then we design crank, and then we design the valves, rocker arms, and other components. So the specs for the gear design, I mean specs for the internal combustion engine design, they will tell us that design a gasoline engine or design a diesel engine, and there will be some power specs, power requirements, and then we will start with the actual design. Any questions at this point? So what I'm going to do is I'm going to give you the design procedure step by step for different internal combustion engine parts. and then we will work out a problem. First, let me show you a very nice picture of internal combustion engine. So this is piston. This piston will have grooves. Typically, there are 3 or more piston rings. The top piston ring is for sealing. The bottommost piston ring is called as the oil ring. This is to scrape the oil, which is on the interface of piston and cylinder assembly. Then this is the cylinder. Cylinder will have water jacket. So because, as you know, during the combustion, the temperature is extremely high and we need to cool it down. So you have the water jacket, that is you have a surrounding the combustion chamber and the piston, so that actually will take the heat out. Then here there is the piston pin. Here there is the connecting rod. And I'm going to show you a stationary engine. So it's not an automotive or locomotive engine. And then there is a cylinder head. And here there is a head gasket. And then you're going to have an intake. You're going to have an exhaust. And then you're going to have a spark plug. Exhaust. Spark plug. There will be bolts. Then this top part would have a particular shape, and there's a reason for that, because this top part forms the combustion chamber. So you would have something called as the hemispherical combustion chamber. That is called as hemi, or you can have particular shape. It totally depends upon the compression ratio, the design of intake and exhaust, and then you will have some valves. And these valves will have cams and tappet, and that will actually open and close the valves. So I'll just name these. Crank, crankshaft, connecting rod, which is also called as con rod. This is piston pin, piston, then this is the cylinder, then this is the oil ring, this is the piston ring, this is the water jacket, this is the cylinder head, these are the bolts, and you have the intake valve and the exhaust valve. So let's start with the design of cylinder. So we will cylinder design is based on two concepts. One is called as the longitudinal stress. So if you look at the cylinder, if you take a cross section of the cylinder, that's how it will look like. So this is the cross section. And usually there is very high pressure here. This is the length of the cylinder. And usually this is denoted as the diameter. So sigma L is equal to P times D, 2 times T, where T is the thickness. So if you think about how this equation came into existence, the pressure is P multiplied by diameter multiplied by length gives you force divided by L times T times 2, that gives you PD by 2T. If you look at the circumferential or the hoop stresses, sigma C is PD by 4T. So if you now look at the cylinder, and take a cross section here, so sigma C is equal to force divided by area, which is P times pi by 4 times D square divided by pi times d times t, that gives you PD by 4. So with this, you can actually look at the longitudinal stresses or circumferential stresses. One thing I want to tell you is the distance between the TDC to BDC is called as the stroke. So let me, so stroke length is the length of piston travel from TDC to BDC, and that is 2 times the crank radius. So say if maximum gas pressure is equal to P, D outside is outside dia of cylinder, D inside or D is just inside dia of the cylinder, T is thickness, 1 by M is equal to Poisson's ratio. Typically, this is considered as 0.25. So there is something called as the apparent longitudinal stress, that is pi by 4 times d square times p pi by 4 the outside square minus d square, which is d square p divided by do square minus d square. And there is something called as the apparent circumferential stress, which is given as d times L times P divided by 2 times T times L, which is P D by 2T. So what this translates into is, if you want to find out the thickness of cylinder, T is equal to P times D 2 times sigma C plus a clearance, where sigma C typically, depending upon the material that you choose, if it is cast iron to an alloy that is used for cylinder, it would go from 35 to 100 Newton per millimeter square. And C is the clearance for reboring. So what happens is, as you use these pistons as cylinders again and again and again and again, after some time, because of friction, the cylinder gets worn out, and you need to remachine the internal part of the cylinder. So that is where we want to rebore the inside of the cylinder, and that actually would increase the diameter and then you will have to actually change the cylinder liner and fit it in, and then you have the cylinder ready to go. So if you look at the table, 32.1, that will tell you the diameter and the value of C. Diameter is 75, C is 1.5, diameter is 100, C is 2.4, diameter is 150 millimeters, it's 4. Now, let's look at the way the engine is generating power. So what we have is, first we have a chemical energy. That is converted to heat energy. This heat energy is converted into mechanical energy. And as these energy transfers occur, you get losses. So we have different types of power. So the first and foremost is something called as the indicated power. This is the power generated in combustion chamber. Then there will be frictional losses. And then what we have is the brake power. This is power at the brake. Or in other words, that is the power that is available. So depending upon what we consider, we have two types of fuel consumptions. So we have something called as the brake specific fuel consumption, BSFC. Fuel consumption. Which is the fuel consumption per unit horsepower. And we have ISFC, which is indicated specific fuel consumption. Which is fuel consumptions divided by indicated power. Efficiency indicated is equal to the brake power divided by the indicated power. And the average pressure inside the cylinder can be calculated multiple ways. So if you consider the pressure inside the cylinder, considering the brake power, which is called as the brake mean effective pressure. Which is the average pressure considering brake power. And indicated mean effective pressure, which is average pressure considering indicated power. So what is power? Power is pressure multiplied by volume divided by time. So pressure is Newton meter square, volume is meter cube divided by time, that gives you Newton meter divided by time, which is seconds. Which is watts. So if you substitute indicated mean effective pressure as power, the pressure that you get here is the indicated mean effective pressure. If you substitute the brake power over here, what you get here is the brake mean effective pressure. And those two are typically defined based on the engine design and the requirements. So let me give you an expression for indicated power. Indicated power, also denoted as IP, is PM L, which is the stroke length, which is the length of the cylinder, area, N divided by 60. This is for 2 strokes. And IP is equal to PM L A N by 2 divided by 60 for 4 strokes. So IMEP is equal to P, L is equal to stroke length, A is equal to area, which is pi by 4, T square, N is equal to speed, and stroke divided by diameter, which is L by D, which is called as L by D ratio, is 1 typically to 1 to 1.5. So what you do is, based on the indicated mean effective pressure, which basically indicated power, we should have an overall estimate of the diameter. We can decide L by D ratio. L by D ratio is the design parameter. So L by D ratio is, let me show you, if you have a cylinder, this is the diameter, and this is the stroke length, L. So L by D ratio is 1. That means it's a square sort of cylinder. L by D ratio, if it is greater than 1, that basically means it's a rectangular type of design. So the next thing is, you have to design the cylinder flange and nut. So this is the cylinder, and what we want to do is, we want to design something like this, which is pi by 4. Force on the cylinder head equal to N times pi by 4 times diameter of bolt square multiplied by sigma T, where N is the number of bolt This is the bolt dia, and this is the tensile stress. And the next part is design of cylinder head. So if you look at this cylinder, what you do is this is the thickness, and the equation is T is equal to D C times P divided by sigma C. D is equal to dia, P is equal to pressure, which is max, sigma C is equal to allowable circumferential shear stress, which is typically 30 to 50 Newton per millimeter square, and C is a constant, is equal to 0.1. So these are the main steps for cylinder design. And what I would do is I would stop here. In the next class, I will work out a problem, and then we can move on to the piston design, and then go on to the connecting rod design, and then we can go to the crankshaft design. So on Thursday, the class would be in person, and I would work out a cylinder design problem, and then move on to the piston design. I'll stop here.